Hi everyone, this is Stephen, host of Computer Art Explorers. Welcome to our Introduction to Computer Programming series. In this episode, we're going to explore how to use integer variables. For the best viewing experience, please remember to watch this video in HD 1080 on a large monitor. Before we get started talking about integer variables, let's just kind of review the fundamental basics of how computers work. Computers store all information at the binary level. That means they store ones and zeros. So think of a light switch in a wall. The light switch is either on or it's off. In binary, we represent the off state with a 0 and the on state with a 1. And then that would translate into a decimal value of either 0 or 1. And that is 1 bit. So think of just one light switch on the wall. Now, if we take 4 bits, that becomes what's called a nibble. Now imagine 4 light switches on the wall. You can have 16 different patterns, okay? It's basically 2 to the 4th power, and here's all the different patterns listed. Now, this effectively in base 2 math, this would be like 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. And then if it's on, like here, 2 to the 3rd power is 8. So there you get an 8, where this is representing 2 to the 3rd power. The pattern, depending on the pattern of the switches, you're representing a decimal number from 0 to 15. In hexadecimal, hexadecimal is base 16 math. It means that one digit is going to have 16 different combinations to it. And the way we represent that is, for the 10, we represent that with an A, and then goes all the way down to F for 15. So you have individual digits. A single digit can represent a value from 0 to 15. Now if we go down to a byte is simply 2 nibbles. So again, think 8 light switches on a wall. And in memory, in the computer memory, it's just like light switches, except they're at a microscopic level and there's billions of them. So the hexadecimal value here, and notice, and the reason why I'm showing you this is because a nibble is represented by 1 hexadecimal digit. So since a byte is 2 nibbles, 2 hexadecimal digits can represent a byte. So here we have this nibble has all ones, which has a value of 15. So that is represented by either decimal 15 or hexadecimal F. So we have the hexadecimal F, and then this nibble is a 2. Okay, if you come up here to this pattern here, there's the 2. And so hexadecimal F2 is then represented by this pattern of 8 on-off switches. If you go into the ASCII chart, I'm going to go to quick reference and look at the ASCII chart, and you'll notice that coming down this column here, where there's the F0, that means everything on this column is represented with a hexadecimal F in the 2nd position. And then on the top row, going across, you have from 0 to F. So F2, if this were to represent a byte of data that was ASCII data, then the F2 would be this character right here, this one right here. Okay, so this will be F0, F1, F2. All right, now let's move down, and right here, we're going to talk about a 32-bit. Well, 32-bit means you have 32 bits, okay, which is also 4 bytes of data or 8 nibbles of data. So when we look at a number like decimal value 0, all 8 nibbles have a 0 value. So in hexadecimal, you can look at the hexadecimal value, like the 0 here is these 4 bits going all the way across. Now, so you have 1, 2, 3. Notice there's 1, 2, 3, and then all the rest are zeros. When you get up into like this nibble here goes to a 1, and then you've got these here, what happens is remember I said 2 to the whatever power. So this would be like 2 to the 0 power, 1, 2, 3. So this will be 2 to the 4th power. Now 2 to the 4th power is 16. And so then you would add 16 plus each one of these 2 to the 3rd, 2 to the 2nd, and 2 to the 1st. Adding all that up, that equals a decimal value of 30. So there's where your representation comes in. Coming all the way over to here, 2 to the 5th power is equal to 32. This 32-bit signed integer, that these 32 bits of data, when they're representing an integer value in memory, this pattern of ones and zeros has a decimal value of 32. And it has a hexadecimal value of a bunch of zeros and then a 2, 0. The largest value you can have that is a positive number would be all ones except the most significant bit. That is used for a sign. So if you notice down here in the negative numbers, this bit is always on for a negative number. So on this number here, with all these being ones, in hexadecimal, this is a 7, right? This right here, this nibble corresponds to that 7. Okay, so 7 and all the rest F's, that becomes a decimal value of the largest decimal value that a 32-bit signed integer can have. And that's the reason why this number is listed right here as the largest whole number that a signed 32-bit integer can hold. All right, so I went ahead and wrote some code right here. And what this code does is it allows us to assign numeric values to A integer, B integer, and C integer, and then print out the name of the variable and then the binary value, the decimal value, and the hexadecimal value of each one of these. So let's go ahead and run it and take a look at it. The value of A integer equals 1, and it's showing you that the hexadecimal value is right here. And it's showing you that the B and C are both, you have a series of zeros and then ones. So over here in hexadecimal, you have 4 zeros and 4 F's. And that's for each one of these. And the reason I wanted to point this out was, notice it's the same decimal value. Let's go back and take a look at the code. And notice here we have B integer equals, and we're using in curly brackets, and 4 hexadecimal digits. So let's go take a look at our hexadecimal numbers. And you can look right here, and you'll notice that both 4 and 8-digit hexadecimal numbers may be used to declare a signed 32-bit integer using the following curly bracket formats. So it's telling you that you can use either 4 hexadecimal digits in a row. And so what I'm pointing out that is if you do that, you're specifying the lower 4. The upper 4 that you're not specifying then would be just zeros. Or you can specify all 8 digits, and you can also take all 8 digits and separate them by a space. Sometimes it's just easier to read it in your code if you have a space there. It's easier for your eyeball to see 4 digits, a space, and 4 more digits. Now, you'll notice that both of these are turning purple, that the Sybos application developer is reading your code and it's detecting that both of these are in fact valid hexadecimal numbers. So that's the reason why it is turning it purple. If we were to take out, see that's still valid, but if we were to take out one more 0 and have 3 zeros and 4 F's, notice how it turned black. So it's black, that's a visual indicator to you, the programmer, that this is not a valid numeric constant. And if you were to compile and run it, you're going to get an error. And I'll just show you that. So let's compile an error. It says invalid hexadecimal numeric declaration. And then it gives you a list of your valid formats. Now, something else I want to point out. Notice here it says variable names must end in the % character. So the variable A, the very last character of the variable name, ends in a % character. Then I read that as A integer, because that means that is an integer variable. And then this here we have equals and then a 1. This is actually called an assignment statement. And you'll notice here that under assignment statements, An assignment statement is used to move data into a variable. An assignment statement takes the form of an assignee variable. So here in this case right here, a integer is the assignee variable. So something is going to get, some value is going to get assigned to a integer because we have a integer equals something. Followed by the equal sign, so this is your syntax, and then followed by a valid expression or a function that returns a result. So in this case, a valid expression, well, this gets into mathematical expressions. For example, you could say 1 plus 5, okay? And that is a valid expression, okay? And let's just go ahead and compile and run this so you can see. So there you go. 1 plus 5 equals 6. 6 is stored in memory, in binary memory, using that pattern of ones and zeros. And it is represented in hexadecimal with that value right there. You could also say times 7. Okay, here we are in section 34, page 1. And you'll notice here, this is your order of operations. When you have an expression, you have operands and operators. So for example here, 1 is an operand. The plus sign is an operator. The 5 is an operand. The 7 is an operand. So we're taking 2 operands and then you have an operator, 2 more operands and you have an operator. So the question is, what operands get processed first? And that has to do with operator precedence. And if you look here, the asterisk denotes multiplication. So this is why 5 and the asterisk symbol 7 means 5 times 7 because of that multiplication sign. Okay, the asterisk is representing multiplication in the computer language. Now, multiplication has a precedence level of 3, whereas addition, where this is being treated, this plus sign is being treated as addition, and addition has a precedence level of 5. Therefore, the 5 times 7 is going to get processed first, and the result of that becomes an operand that then gets added to 1. So if you do this in your head, 5 times 7 is 35, plus 1 is 36. So there you will get a correct result. Let's go ahead and just run this so you can see it. And so there's your 36. If instead you wanted to actually do the 1 plus 5 first, you would have to put the 1 plus 5 in parentheses. That parentheses overrides precedence. It means execute everything inside the parentheses first. So whatever's in the deepest set of parentheses would get executed first. For example, we could do all of that, we could do all of that, and then we could say take the entire result to the power of 2. Okay, now let's go back and take a look at our manual, and you will notice that the exponent right here, exponentation, has a precedence level of 2. That if we did not put those parentheses in there, what would happen is the very first thing that's going to happen is whatever's in the deepest part of the parentheses gets executed first. So in this case, the 1 plus 5, that would get added together, that becomes 6. Then with no other parentheses, multiplication has a precedence level of 3, whereas exponentation has a precedence level of 2. So the 7 to the power of 2 is going to get processed, which would be 49, and then that would be multiplied by the result of this 1 plus 5. So you would have this being multiplied by 7 to the power of 2. And again, if you wanted to change that, let's say we wanted to take all of this to the power of 2, we would have to then enclose all of this in parentheses. So now what happens is what's called the deepest nesting would be right here. The 1 plus 5 is the deepest nesting. This is nested inside of this right here. So these outer parentheses, then you have inner parentheses. So it's nested inside the inner parentheses, gets processed first. Then everything within this gets processed, and then the result of all of that gets taken to the power of 2. So if we were to run this, the way you would read this is that 1 plus 5, the result of which times 7, the result of which gets squared. And we could run that and you'll see the result. And so there's your result, 1764. So if you were to bring up a calculator and you wanted to confirm that that is correct, 1 plus 5 is 6, right? 6 times 7 is 42, and then 42 times 42 would be the power of 2, right? Or you could say x to the y and put it in there to the power of 2 equals, and there's your 1764. So that's just a way to verify that yes, it is actually doing it the way you wanted to do it. Now, what's you need to understand is just because I've used numbers in here, you could also use variables. For example, I could have said z integer equals, let's say 5, and then instead of having that 5 there, we could have had z. So when this expression gets evaluated, whatever the value of z is going to get plugged in to this part right here, and it's going to get processed or evaluated to wind up with a result that then gets assigned to A. All right, to provide a real-world example of when you're going to be manipulating data inside of an integer variable, what I did is I created some code here, and what this code is going to do, it's going to tell the user to press any key, and when the user presses that key, it is going to read the data out of the buffer, assign it to this variable, and exit the loop. And when it comes down here, the data, and notice that this is an integer variable, it ends in the %, this data is going to get assigned to A, and then it's going to get printed out. The next thing I did is I said shift right A integer, the value of A integer, by 8 bits. So in this case, what happens here is this raw keyboard data, that is right here, this 32 bits of data. If you notice, this byte right here, these 8 bits that are listed as A, that's going to be something called the key code. That's a quasi-ASCII. The next section here is the V. The V is the virtual key code. So you have a value from 0 to 255. It just happens to be pushed into this section of the 32-bit integer. Okay, that's where this virtual key code is at. So let's just go ahead and take a look at this. I'm going to go ahead and compile and run it. Now on the keyboard, I happen to have the num lock on, and I'm going to press the 5 on the numeric keypad. The 5 on the numeric keypad is not the same as the 5 that is above the R and the T on the regular part of the keyboard. And sometimes in a program, you might need to distinguish between the two. Did the user press the 5 that is above the letters in the keyboard, or did the user press the 5 on the numeric keypad? So I'm going to show you how you can in fact make that determination. And notice here, right here, what we have. Now what I'm going to do is I want to show you the code while we're looking at this. So I'm going to do a trick. I'm going to hold the control button down, and I am going to click on this, and it just says here that the master runtime window text grid copied to the clipboard. So all of this text here just got copied to the clipboard, which means I can come down here and I can paste it. Okay, so now we can look at our output data with our code at the same time. And let's go back and take a look at our manual. So here is this outputted value. Click on this and let's bring this up. I'll put this in a remark. Okay, and what I'm going to do is I'm going to separate this to make it easier to read. Okay, so here we have right here our virtual key code. Remember, this is hexadecimal, so these 2 digits are going to represent the A. The 6 and the 5 are going to represent the V. So there's something called a virtual key code. And let's go and take a look notice right here, I'm on section 36, page 5. And the virtual key code that is a 6 and a 5 hexadecimal, and I'm just going to come down here to right there. Notice what it says, that it's VK numpad 5. So you could actually say VK numpad 5. Whoops. There. And notice something else, that the language, the Sybos application developer, is recognizing this as a valid keyword constant. Okay, so if we were to set, for example, let me go and mark this out so I can come back to it. What I'm going to do is I'm going to say B equals this numeric keypad, right? So I'm going to run it again. Oops. See, I got a bunch of errors because I can't have that just hanging around up there by itself. And I need to remark these lines out because that is not valid code. I still want to see it. So by adding the apostrophe character, it just turned all that into remarks. And let's go ahead and just compile and run it again. Okay, again, I'm going to hit the 5 on my numeric keypad, and just so you guys know, you can't see it, the num lock is on. I hit that, and it created the same thing for us. So notice the 65 right there, right? Well, under B, here's the 65, all right? Now notice what we really need to do if we want to compare, and we really want to say, we want to test whether or not the user hit that 5 button. Then what we need to do is we need to take these 2 digits right here that's in this raw data, and we need to shift them to the right by 8 bits. So let's go ahead and do that. What I'm going to do is I'm going to remark this out, come down, bring this back up, and unremark these 2, and then I'm going to show you something, and that is that the shift right, if we go take a look at this, and let's look at it in the manual, shift right. So shift right is going to take all the bits and shift them right by however many you have here. In this case, it's going to be 8. So it's going to shift them all over by 8. So let's go ahead and compile and run this and take a look at it. Again, I'll hit that 5. So there's your raw data. Your raw data shifted over 8. So notice we have the 6 and the 5 there, but we also have all this other data. Okay. Now, if we want to strip all the rest of this data out so we have a value that we can compare against our virtual key code that we want to test for, then we need to strip out all the rest of this. And the easiest way to do that is with this AND, where it's C integer equals B integer and we have the F and the F. Okay, to explain how this ampersand works, and notice right here, the symbol, the ampersand, it means conjunction, okay? You can actually use the word and, or you can use the ampersand. Either one, it means the same thing, okay? That is an operator. AND is an operator, and it is identical to the ampersand sign. So there you can use them interchangeably. The OR can be used interchangeably with the pipe character, okay, for an exclusive OR. So what this is going to do, all right, let's just go ahead and run this. Again, we're assigning to A the value here that is going to get shifted over by 8. So it's going to take that 65 and move it over. And so that's going to be A, and then we're assigning a fixed value of FF to B. And then C is going to be the A and the B. So let's take a look. And what you have here, notice the 65, and then we have this other stuff here that we want to clip off or get rid of it. And here we have FF. Notice here's all your ones. Well, what the AND does is that it's a bit comparison. So it looks at this bit right here and this bit, and it says if the bit here is 1 and the bit here is 1, then the resulting bit is 1. So anywhere you see a 0, you have a 0. Notice over here, it's a 0, 0 equals 0. Okay, so it's literally going down each one of these. And that's what how this works. So by having FF, it means we want to have all the bits, whatever bits are in this location and this location, and we want to effectively mask out all the rest of it. So we're going to, with this being zeros, it basically acts as a mask that mask out all this data, and it only drops in just these two right here, these two digits, whatever these digits are. And so that is the cleanest, easiest way of getting rid of the rest of this so that we have a value that we can then compare to, in this case, the numeric value of the VK numpad. All right, so now that you understand the concepts, this is some example code of how this would actually be used in a real-world example. You're grabbing the raw keyboard data, and here you have shift right. You're taking the keyboard data, you're shifting it right by 8 bits, and then you're taking the result and doing the AND with the 00FF. So again, we're just going to have the result be whatever the virtual key code is. And we're going to compare the virtual key code result with the fixed value of VK numpad 5. So we're testing. What this is basically going to do is going to return a true or false value. True being represented by 1, a false being represented by 0. And if the user did in fact press the 5 on the numeric keypad, then it's going to be true. Where if the user pressed any other key on the keyboard, it's going to be false. So if in the if-then statement, if the result is true, then this gets executed. So that's why it's going to, if the user did in fact press it, it'll print off the user pressed it. And if the result is false, it will execute this else statement, which is the user pressed some other key. So let's just go ahead and run this so you can see it. Now I'm going to press the 5 that is on the numeric keypad, and it tells you, yes, the user did press that particular key. And I'm going to go ahead and rerun it and press the 5 that is over the R and the T on the regular part of the keyboard. And it tells you the user pressed some other key. So there's a great example if you ever need to distinguish between the two, how you can do that. So I want to point out one other thing, and then we're going to go on to something else. And that is, if you notice here that I have put in parentheses all of this, if I take these out, it won't work properly. And let me show you why. That is because, see this equal sign here? This is what's called a relational operator. It's going to compare the relationship between the operand that's on the left side of the operator with the operand that's on the right side of the operator. And if you notice, the equal sign is right here, and it has a precedence level of 6. However, this ampersand sign is down here, and it has a precedence level of 7. So we want all of this right here to be evaluated first, right? We effectively want to mask that out and then compare the value of this that has been masked out with this. So that's the reason why we have to put that in parentheses. All right, this next section of code right here, we've created this code so that we can explain the difference between subtraction and negation. Notice that the precedence level is different. If the minus sign is used as a negation operator, it will have a precedence level of 1. Whereas if it's used as a subtraction, okay, it will only have a precedence level of 5. So here's where this comes into play, and I'll explain how to tell whether or not the minus sign is being used for negation or for subtraction. right here we have C, and this expression is minus a integer to the power of b integer. So a integer is 3, b integer is 2. So effectively, and this is a remark here, effectively the expression is minus 3 to the power of 2. Okay, but here's the catch. Normally, some people are going to say, well, if you take 3 to the power of 2, if the minus sign is subtraction, then you use the exponent first. So it would be 3 to the power of 2, which would be 9, and then you would subtract it from, I guess, nothing, because there's nothing before it, and you would have minus 9. But in fact, that is not the result we get. I'm going to go ahead and compile and run it to show you, okay, that you get a 9. And the reason you get 9 is this is being treated as negation. All right, it has a precedence level of 1. So the value of A, which in this case happens to be 3, is being negated first. And then that value, which happens to be a minus 3, is being taken to the second power. So minus 3 times minus 3 would in fact be positive 9. And that's the reason why the result is in fact positive 9. The reason why it's negation is because there's no operand before the sign. Before the minus sign, there's no operand, and that is the key reason and the only reason why it's being treated as negation. If there is any operand ahead of it, the minus sign will be treated as subtraction. For example, if we had 0 minus a to the power of b, now this minus sign will be treated as a subtraction operator. And because of that, 3 will first be taken to the power of b, which will result in a 9, and then 0 minus 9 is negative 9. So I'm going to go ahead and rerun this to show you. And there you go. So just understand that if you create a statement like this, negative a to the power of b, if you want this a to the power of b to take place first and then the entire result to be negated, again, you need to put that in parentheses. Okay, so enclose this in parentheses, and then that will get done first, and then the result will be negated. And I'll go ahead and run that so you can see it. And there you have your negative 9. Okay, next we're going to discuss something called positation. Positation is when anytime you put a plus sign without a leading operand. So if there's no operand, just like in negation, if you don't have a leading operand, then the minus sign is treated as negation. Well, if you don't have a leading operand, a plus sign is treated as positation. Effectively, nothing happens. In a lot of computer languages don't even allow this syntax. It throws a syntax error if you try and have a plus sign without a leading operand, because it just really doesn't know how to process it. But mathematically speaking, if you have a plus sign without a leading operand, effectively it's a declarative statement. It's like you're declaring that that value is positive. And where that comes in is, let's say you have a string of numbers that are both positive and negative, and you want to declare in your number, maybe you have, let's say, a 37 minus 29 and a positive 12. Okay, it allows you to definitively declare that the 37 is not a negative number, that there's not a typo. Okay, versus just having it like that. Okay, just 37 like that, it's like, oh, well, did somebody forget the minus sign? This allows you to declare the fact that this value is in fact a positive value. That's really the only reason why it exists. It doesn't, other than that, really affect anything. I'm going to go ahead and just compile and run this to show you. And there's your 37, your minus 29, and your 12. All right, next we're going to talk about integer division. So let's take a look at what this is. This is called, again, an integer assignment statement. And the reason is that the assignee variable, That's the variable right here that's receiving the value of the expression. Whatever this expression is, it's going to get evaluated. The result of the evaluation is going to get assigned to a variable. And in this case, because it happens to be an integer variable, that means that this entire statement or expression has to be an integer expression. Every operand must be an integer value. And if it's not, you will get an error. So I'm just going to go ahead and compile and run what we have here. So 1 divided by 3 in integer math, the decimal value, it's showing 0. I'm going to explain why you're getting these results. That's because an integer cannot hold a 1/3 value, nor can it hold a 2/3 value. And some people might say, well, how come that doesn't round that off to 1? It should round it up. There's a reason it doesn't round it up. The pure result of that integer division of 2 divided by 3 is in fact 0, and there is a remainder. Now you can access the remainder with modulo operator. And then of course 3 divided by 3 is in fact 1, so that's the reason why you have a 1 here. Let's say if we were to say A equals 2 divided by 3 and B equals 2 mod 3. And let's run it. And so 2 goes into 3 0 times, but has a remainder of 2. And there's where you're getting your remainder on your modulo. So this is working because in integer division, it is not generating fractional values. All right, next we're going to talk about invalid integer operands. Right here we have C integer equals 0.25. Now, 0.25 is a decimal value. It cannot possibly be held by a signed 32-bit integer. And because this value cannot be represented in this integer format, it is invalid. And what's going to happen is, it's going to compile and run this so you can see. And the compiler, if I click on this, it lights up the line, and it's telling us that we have a bad numeric constant. So this is the constant value. It's a numeric constant. And it's telling us the value is invalid when used in an integer assignment statement. And that's what this is. This is an integer assignment statement. Now, if we want to actually use the value of 0.25, we need to use a floating point variable. So I'm just going to say D equals, and I'm going to bring this up here. And then I'm going to put D down here, just to show you guys something. And that is, when we have the D up here, this is a floating point variable because it does not end in the percent sign. And notice that's the only difference. A variable, if it ends in the percent sign, it means it's an integer variable. Okay, so the compiler is going to allow this because this value can be held by a floating point variable. So in a floating point assignment, all right, that is valid. All the operands are allowed to be floating point values. So the compiler is going to run this, and when this program gets executed, the floating point value of D is going to be 0.25. So the compiler has no way of knowing what D is going to be when it comes time to execute this. So the compiler lets you compile this code. But I'm going to go ahead and compile and run it, and then we're going to see what happens. So it compiled, and then it started running. And as it was running, notice that the runtime engine threw an exception. And it's telling you that at line number 13, it experienced an integer expression error. And it's telling you that the value of the float variable cannot be held by an internal integer variable. And again, it's telling you that happened on line 13. So if we go into our log, and I click on the log, notice all the line numbers here. You can go down, and this is how you can figure out in runtime, when you're having runtime errors, where the error is in your code. Look at the log. Here we are on line 13, and we know that that error is regarding this section of code. So we know that D cannot be used in this expression. This is an integer expression. So let's go back to the source code, and somebody's going to say, well, what if I just take it and I multiply it by 4? Well, you know, if you take a quarter, multiply by 4, the result's going to be 1. We know that the value of 1 can be held by the variable C integer. Now I'm going to compile and run this, and you're going to see that it still throws the error. And the reason it still throws the error is because every operand within this entire expression, this is an integer expression, every operand has to be able to hold an integer value. Okay? You cannot do intermediate math in an integer assignment statement. However, if you need to do this, there's a simple fix, and that is just use the int function. And I'm going to go to the int function, and I'm going to show you what that is. Notice the int function, the first parameter, it says float 1. Okay, well, float 1 just means it's the 1 means it's the first parameter. Right? If you had comma, if you had another parameter, it would be the second parameter. The float part simply means it's a floating point expression. So it will take this, and this will get evaluated using floating point math. Then the result of this will then be, and this shows you the logic used by this, and basically uses this logic to test whether or not the value can actually be held by an integer variable. If it can't be, then you have an overflow. Because, this could be 0.25 plus e to the 304, which is a monster number, and it can't hold it, so it's going to generate an overflow. And especially if you multiply that by 4. But let's just go ahead and compile and run this so you can see the different type of error. Okay, and again, the error number is different, but it's showing you that it's an overflow, and it's showing you that the rounded result of the int function will not fit in an integer variable. So it's telling you what the problem is. But if we take off this e to the plus 304, we drop that back out. Now we run it. Well, 4 times a quarter is going to be 1, and it's going to assign 1 to C, and that's going to work just fine. Okay, so there you go. So a lot of times you're going to be using stuff, want to do things in floating point math, but then need to have an integer value to feed into some kind of a function. For example, I'm going to show you on the print binary. Okay, notice here what it's telling you, that int 1, it's telling you this has to be an integer expression. Okay, so I have an integer variable here, that's fine. But if you wanted to say print binary of D, okay, so, all right, so we're going to print the string result. So again, here, you're going to wind up with this other error code, this 46. And it's telling you that the value of a float variable cannot be held by an internal integer variable. And again, what is it talking about? It's talking about this value right here. It's this D, because the parameter is an integer expression. You have to have an integer expression, which means every operand in this expression has to be held by an integer variable internally. So you could say D times, and again, you could hear D times 4. And this is any kind of a valid integer expression where you have an int 1 will work. You could say, plus 7 divided by 33. Okay, you could do something like that. That's all going to work as long as this D is a number that can be held by an integer operand. So let's take a look at what if you had D equals 25. Okay, if you have D equals 25, that's going to work. There's times in computer programming that you absolutely want to use integer mathematics and you need integer expressions, and there's times you need to use floating point math and floating point expressions. Okay, next we're going to talk about using numeric format schemes to print out formatted integer data. So here we have an integer variable grapes, and we're assigning the value of 1,234 to this variable. If we just print it out, just say print grapes, I've got the arrows here so that if there's any leading or trailing spaces, you'll be able to see those. So let's just go ahead and do that and pay attention to that line. I'll go ahead and compile and run it. Notice what's happening. It is printing the value, and then it's adding a trailing space. Okay, I'm just going to go ahead and copy the output into the source code so we can take a look at it. So here we have a trailing space. So by default, if you just print an integer value, the runtime system is going to add a space. Now I created a numeric form using the same thing that is the default, just to show you that this is what the default is. So let's go back and take a look. Here in the manual, we have open numeric format scheme. And the first value right here, the int1, that is the fixed field size, or null if it's not fixed. So null is the same as 0. So here, that means not a fixed field. The number of leading spaces, the number of trailing spaces. So no leading spaces, 1 trailing space. And then 1 or more NSF prefix flags. So there's no prefix flags being used. For example, the show commas flag will insert commas into it. So if we go back over here into our manual, decimal string internally, okay, when you just say print grapes and just prints out grapes just like that, if you don't use this decimal string internally, it's using these exact parameters right here. That's what's called the default format, and that's the reason why by default you're not getting any commas and you're getting 1 trailing space. If you want to change that, let's say if you didn't want any trailing spaces, well then you could create a format scheme that didn't have any. And I'm going to go ahead and run that so you can see that. And that was scheme NF00. So notice the trailing space has been removed. Okay. Now here's what we're doing is we're creating a fixed field size of 14. Let's go back and take a look. Notice the fixed field size in characters. So this is going to guarantee that no matter how big or how small the number is, it's going to set that number into 14 characters. Okay. Now if you don't give it enough room, it's going to throw an error. For example, let's say we only give it 5 characters to put it in. Okay. And well, I'm going to compile and run this because 1, 2, 3, 4 will fit in 5 characters. Even with a comma, it fits. But if we made it 4 characters, and then we compile and run it, notice it's throwing an error. This will fit. The 1, 2, 3, 4 will fit, but the moment we try and add a comma to it, it's telling you that there's an out of bounds error. Okay, that the formatted data is too long to fit in the NSF specified fixed field size. So there's your error. Let's go take a look at these flags. Okay, one of the flags that you can use is don't throw numeric formatting errors. I'm going to copy this flag, and I'm going to use the pipe character. Put this on a different line here. Okay, I'm going to use the pipe character so that we're now specifying both the show commas flag and the don't throw numeric formatting errors flag. Let's go ahead and compile and run this. And it just fills it in with pound signs, indicating that it cannot format that. So that's a way that it's visually representing that you have a formatting error without crashing the program by throwing an error. Now, of course, your program won't crash if you catch the error and you deal with it, okay? But that gets into error handling. Before we go any further, because we are talking about integers, I want to kind of explain what is going on with these flags. Okay, so I set up an example right here, and then we're going to pause it. And what we're going to do is we're going to print the value of the NSF show commas, and I'm just going to print it, the binary value of it. And so we're going to show the binary value of this flag, the binary value of this flag, and then notice I'm using this pipe character. So if we go over into the manual, notice down here where the pipe character is the or. Instead of doing that, I could just use the word or, okay? It means the same thing, okay? And it is binary, all right? All of these work on integer math at a binary level. Okay, so you can use the pipe character, and I just want to show you how this works. Let's go ahead and compile and run this and take a look at it. So here what you have is the NSF show commas. This is called a flag because this bit right here, see the 1? Notice that all the rest of them are zeros. That's because this bit turned to 1 is indicating to this function, the Open Numeric Format Scheme function. And if we bring this up and we look at this, notice what it's telling you under parameter number 4, 1 or more NSF prefix flags. So you can specify multiple flags, all right, and just pass a integer value in at this level, and whatever flags are turned on, that's going to control how the thing prints out. So every function that uses flags, the flags are going to be predefined by that function to have certain meanings. And in this function, the Open Numeric Format Scheme function, it uses these NFF prefix flags so that you, in your code, like for down here, you want to open up a numeric format scheme, you want to use the show commas flag, you want to use the don't throw numeric formatting errors flag. That's the two things you want to do. But what I'm showing you is how this works mathematically, so that you understand what's going on by using this pipe character. So let's go back and take a look at this one more time. And so the NSF show commas, here's a 1 here. Notice the NSF don't throw numeric formatting errors. The flag that represents that is right here. Okay, so think of each one of these bits as individual flags. So when you pass a value, in this case I just use the integer value flags, you want to pass that value and you want to have both of those particular flags turned on and everything else turned off. And notice how the 1 got dropped down, this 1 got dropped down. That's because that pipe function, being the inclusive OR, means if either bit is a 1, then the result is a 1. Okay? So if they were both 1, if there's a 1 here and a 1 here, you'd still have a 1. And that is exclusive OR logic. So this is at a bit level, and I wanted to explain that because this is using integers, and whether you may not realize it or not, when you're specifying flags and you're using the pipe character to separate the individual flags, the reason that works is because it's taking the numeric value and it's using the inclusive OR with the next one, and you can do that on and on and on. And because you can use the inclusive OR as the last character on a line, comments notwithstanding, so you could still have comments like you still have a remark indicator right over here, and that would still work, whatever you want. And then you could have, let's say you want to have a third, maybe you want to say right here, use 2 decimal places. Okay, so you could do that, and that would work. You have 3 flags. Let's just print this out and you'll see. Okay, so notice here on the round off to 2 decimal places, what you have here is you have a flag. What this is actually means is this flag here is telling the function that, hey, we want to round off, and the value of this right here is telling it that we want to round off to 2. Notice that that is a 2 decimal places. If you wanted to round off to, let's say, 8 decimal places, you'll notice something, and that is that flag is still on, but you'll notice this now, this happens to be a binary representation of 8. So this part isn't actually being used as a flag. This is the flag, and this happens to be a value that if this flag is turned on, then it reads this and takes this as the value that it's going to use for how many decimal places it's going to round off to. Okay, and the last thing I want to touch on in this video, I just want to bring your awareness that something does exist. Something called a print channel exists, and that you can actually use print channels when you print your data out. Now, there's some concepts here that are actually beyond the scope of this particular video, such as a VTG, that's a virtual text grid. Technically speaking, when you print data, you're printing it not onto the screen, you print it into a text grid, and then the runtime window displays the data that's in the text grid. But I want you to be aware of the fact that you can create a print channel and you can assign a print channel a particular format scheme that you've opened up. So in this case here, the NSF2, if we want to use that formatting scheme, we can either just print normally and then use the decimal string every time and specify which numeric scheme we want to use, and that will convert it into a string data that then prints out. Or we can assign this numeric format scheme to a print channel, and when you do print #PC, what this is doing is this is saying I want to print data to this print channel. Now, print channels can direct data to a file, can direct data to a raw printer that you've opened up. Could be like a label printer or something like that. And in this case, it can print to VTG, which is a virtual text grid. And there's a bunch of different options. I'm not going to get into all the different options on this, but there are different options that you can create for print channel. And in this case, what I want to point out and show you that it's doing is that when you print out the number grapes, the number is always going to be formatted under the scheme that was specified. So because we're specifying scheme 2 here, just by printing out using this print channel, it's going to be the same as this. Let's go ahead and run that and you can see that. Okay, so there you go. And with that, that concludes this video. If you guys like this video, go ahead and give it the thumbs up. If you like the channel, go ahead and hit that subscribe button, and cheers.